as well. Okay. Good afternoon all, and we start the fourth session of the material joining lab in this semester. So today we have lined up one interesting demonstration. During the first introduction class, I showed you one unique simulator. Okay, the simulator which can be used to physically simulate various thermal mechanical cycles a metal or alloy sample is subjected to when it is actually processed in various metallurgical operations, including rolling, forging, continuous casting, and welding. So we are going to see how this equipment, which is known as Gleeble thermomechanical simulator, okay, is going to be used to simulate heat affected zone of a weld. Okay, we have lined up 5 interesting experiments. You remember last class when we carried out a gas metal arc welding, so we also measured a temperature cycle in a heat affected zone by attaching a thermocouple. Imagine, suppose in real life we want to simulate how the microstructure evolves in that location of a heat affected zone. We cannot keep doing welding, and after welding we'll have to do the cross section and look at the micro only in that location. So what we can do is we can simulate such conditions, okay, in Gleeble to understand how the microstructure changes when we subject that material for a typical weld thermal cycle. Okay, so this can reduce the number of experiments, number of welds, number of expensive equipment we need to use, okay, and the consumables we may have to use in real life. So therefore, while developing a welding process or welding procedures, this Gleeble simulator is extensively used to arrive at suitable process parameters for a given welding condition to achieve microstructure which can withstand the service load. Okay, so we have lined up 5 experiments today. The first experiment, okay, we are going to show you how when we simulate a sample and we measure the temperature of the sample at a location. Okay, so we generally spot weld a thermocouple, and the spot welded thermocouple would be attached to a sensor, and that would be controlled by an industrial computer in a system. So we can program the required heating and cooling rates which can be subjected on the sample. So the first demonstration we'll see the thermocouple welding. Okay, it is also welding, right? So we will do spot welding of thermocouples onto a sample. Okay, so that's the first demonstration. The second demonstration, okay, we will see how the thermal cycle which we have measured last week when we have carried out gas metal arc welding can be used to simulate, okay, the heat affected zone. So we will feed the data which we recorded during last week experiments in a gas metal arc weld, primarily when we carried out a constant current, okay, gas metal arc weld, and in control metal cold metal transfer, CMT, control deep short circuiting transfer mode. So the thermal cycles which we measured, we would subject, okay, a sample with that thermal cycle in a controlled manner here. Okay, and that's the second experiment. The third experiment, okay, we will simulate heat affected zone of a resistance spot welding. Okay, the actual demonstration of resistance spot welding we will see in subsequent weeks, but the heating and cooling rates that are subjected in the heat affected zone of resistance spot weld would be at least 3 or 4 times higher than what we expect in gas metal arc weld. So we would also demonstrate how extremely fast heating and cooling, okay, in the range of 1000 centigrade per second, okay, we can still achieve that using this equipment. How such a fast heating rate can be achieved, and then how fast we can control the entire simulation cycle. Simulation here is not mathematical, physical simulation. Okay, so that would be the third demonstration. So first demonstration is thermocouple welding. Second demonstration is the actual temperature we measured during last class. We subject okay, that thermal cycle into a sample. The third is a simulation of resistance spot welding thermal cycle. And then the fourth demonstration we are going to look at in a solid state welding process such as friction stir welding, okay, and heat affected zone, we generally call that as a thermomechanically stir zone, TMS zone. Okay, why? Because in those regions we not only increase the temperature, there is also mechanical deformation. So therefore we need, in order to simulate those zones, we'll have to subject both thermal and mechanical cycle. So we will also heat up and then apply a load, strain, and then cool down. So we have measured such thermal cycle, thermal mechanical cycle in a friction stir welding, and then we would also see how those simulations can be carried out by simultaneously applying both temperature and a mechanical cycle. Okay, so that would be the fourth experiment, right? And then fifth experiment, what we are going to do is dilatometry. So what is the dilatometry? So dilatometry we carry out, okay, to understand the changes in the sample dimensions, isn't it? So imagine if you want to calculate the thermal expansion of the sample. Okay, so we'll have to attach a sensor which can closely monitor the changes in the sample dimensions. Okay, so imagine if you want to understand phase transformation behavior. Okay, so when you take a low carbon steel, iron carbon system, you heat up. Okay, so you expect a thermal expansion, but when the crystal structure changes from one phase to other phase, you see changes in the volume. Okay, that would be reflected in the dimension of the sample. Okay, so by attaching a sensor, which is nothing but a dilatometer, okay, and it's an LVDT, okay, so and a strain measurement system which can measure precisely in the microns the changes in the sample dimensions in diametric C strain or L strain. Okay, so we would attach a C gauge, okay, to measure the changes in the diameter of the sample, and then demonstrate how we can track, okay, the sample volume change when we apply a thermal cycle. So we heat up. Imagine, so you start with iron carbon alloy, 0.1% carbon containing steel. When you heat up, what happens? So you go to an austenitization region. The moment the BCC ferrite changes to FCC austenite, okay, there will be volume shrinkage. So then the sample dimension will reduce, diameter will reduce. So that would be picked up by the dilatometry. Okay, and then subsequently we can heat up and fully austenitize, and then we can track the thermal expansion, and then subsequently we can cool down. So when you cool down, when the FCC again transforms back to BCC or BCC plus cementite mixture or a martensitic transformation, there will be volume expansion. So the diameter will increase. So we can track the change in dimension. Precisely temperature at which dimension changes is the onset of transformation. Okay, so with this demonstration you will also learn how we can calculate, okay, the transformation start in temperatures of various allotropic transformation. Right, so that is the last demonstration we are going to look at. Okay, so we will be heating up and then cooling down at a given heating and cooling rates, and then you would see the changes in dimensions by dilatometry and how that can be used to arrive at transmission start and end temperatures. And that dilatometry experiments are widely used for various applications to optimize heat treatment procedures or to construct CCT diagrams. Okay, so we can subject to various cooling rates and understand for a given cooling rate what transformation, okay, we may expect. Okay, so this is the overview of today's session, and today's session would primarily be conducted by our technical superintendent, Mr. Rangan, okay, who's actually mans this Gleeble lab, who is also one of the experienced Gleeble operator in the country. Okay, and I just want to take another note of this. You won't see this demonstration many places, because it's one of the equipment which is fully functional, touch wood, okay, in India, and globally there are about 30 systems, okay, about and around 35 systems only. Okay, so therefore this demonstration, it is very unique. You won't see these regularly. Okay, in India there are only 2 places right now it is operational in academic institutes. right? So therefore, okay, please be attentive. And if you have any questions, you can ask either me or Mr. Rangan. So I may be away because I got an urgent call from director's office, so I may have to rush. Okay, but Mr. Rangan anyway will be manning the session. Okay, any questions on last class or today's demonstration? In GMAW arc initiation mechanism. Okay, so arc initiation mechanism GMAW is by short circuiting. Okay, so you need to understand the concept of breakdown voltage. Okay, so the arc initiation by definition is actually carried out, okay, by the emission of electrons from the cathode. The moment the cathode is conducive enough to emit electrons, and that condition is, we call that ignition moment. Okay, moment of arc ignition. Okay, suppose if you are setting the electrode as a negative, okay, so then electrode is a cathode, right? So then what is the primary function of cathode is to emit electrons, and a material can emit electrons by two ways, by thermionic emission or field emission. Okay, so in order to create that condition for electron emission, so we'll have to do some trick. So in gas metal arc welding, if you look at the slow high-speed video in slow motion, okay, so the moment the arc is getting initiated, the wire touches the base plate, okay, and then because of the contact resistance between the surface of the plate and the electrode, the temperature at the interface would increase significantly, okay, and then slowly we retract the wire, okay, to form a liquid bridge, and then the temperature at this liquid bridge, because of the bridge formation, would go tremendously high, and that would lead to increasing in temperature, and therefore, and that subsequently when the wire is retracted, the tip of the electrode would reach the condition to emit electrons by thermionic emission. Okay, so that would trigger the avalanche reaction inside the gas medium, the gap between the tip of the electrode and the workpiece, and that would lead to the arc ignition. And this method of igniting arc is widely used in a consumer welding process. Like for example, gas metal arc, the first demonstration we saw, manual metal arc. Imagine, so when you recall, so initially the technician was striking, isn't it, touching the electrode with the base material and slowly taking out. What does it say? So that is how we ignite the arc. Okay, in gas tungsten arc welding, arc ignition is primarily by the mechanism what is called breakdown voltage. Okay, so or we can also do high frequency ignition. Okay, so that is another mechanism. Maybe you can look at some of my YouTube videos on NPTEL, so it will be clear. Yeah, Alakya, it's clear. Any other questions? Okay, so if not, I will continue. So we'll start here. Anyway, I will try to come back to get some, if you have any questions later. If not, I will see you next week. Okay? Yeah. Okay, go ahead. Yeah, Mr. Rangan, sir.
Yes, sir.
Yeah.
With these experiments, had I close the gasket? Okay. Then I'll be doing it and I'll be explaining.
Sure. You need to unmute.
Yeah. No, I can't. Thank you, sir. So, good afternoon, students. Hello, I am audible?
Check, you need to start the video. What is it? Video you need to turn it on. Hold on. Oh, yeah, it's coming. Okay, so follow Jack Parviz's theme. Yeah. Go. Go ahead, sir.
Yeah, so good afternoon, students. So I have to say first of all special thanks to Professor Murugayan. So he has explained the introduction, given introduction, very nice introduction about our Gleeble equipment and what all the applications we can do with this physical simulation with this Gleeble. And thank you, sir. And he has explained about what all the experiments today we are going to handle do with the Gleeble experiment. So we have planned for about 5 experiments. So one after one I will be explaining you how to do that experiment and all. So please follow it. And first of all I have to tell about the heat affected zone. So why do we want to do a heat affected zone with this Gleeble simulation? So when you look into the heat affected zone, let's take an example of a GTAW process. When I do that, so my heat affected zone will be less than 0.5 millimeter. So I cannot do a further analysis. So to have an elaborate analysis in a heat affected zone, so I'll be doing a physical simulation with our Gleeble machine. So let's see how this can be done. And this Gleeble machine is capable of doing with all our welding processes. And as an engineer as well as an welding engineer, we have to be proud that initially this Gleeble is designed for our welding simulation. So then after slowly the other applications have been incorporated into this machine. So likewise, if we see the different welding processes, so each welding processes has got a different heating rate. Like our manual metal arc welding, if you take that, so that heating rate for manual metal arc going to be around 40 to 50 C per second. And likewise, if you see an CMT or GMAW, will be going to be a 60 to 80 C per second. And then GMAW, it's called a TIG welding. So that will have an around 100 C per second. So likewise plasma also we have, plasma welding we are going to see the next week. So that will be around 300 to 400 degrees centigrade. And if you see the resistance spot welding will have a very high heating rate. So it's going to be more than 1000 degrees centigrade per second. And then the laser beam welding we have. Then after the electron beam welding. So these two welding processes are going to be more than 3000, 4000 C per second. So all this welding high heating rate as well as a low heating rate can be done with our Gleeble equipment. So first of all, initially I will be talking about our Gleeble equipment. So let's see each and component of our Gleeble equipment. So initially we will have a tour of our Gleeble equipment. So please follow us.
Yeah.
Okay, so where you can see our Gleeble equipment. So here we have different parts in this Gleeble equipment, where you can see the tower, which is the console unit.
Hold on, sir. Yeah, I think the video is not there.
Okay. So where you see the console unit, where you can all the controls have been done in this console unit. Hello? Yeah, video is coming.
Your video is coming. Prakash.
Yeah, Prakash is coming.
Can you make an announcement that they can look at Prakash video?
Yeah. Students, you can see the Prakash video.
Yeah, go.
You able to watch? Yeah, okay. So, okay, thank you. And my voice is good? It's audible? Hello? Okay, right. Right, so where you can see the console. where all your controls can be done with this machine. And the left hand side of this machine will called, normally we say it is called a load unit. And this side right hand of our load unit, it's going to be a pocket job or a mobile conversion unit, which you can do a chamber we have. Inside this chamber we are going to fix our sample and other things. Apart from this, we have an desktop computer. So where we can program our the simulation, whatever we want to do, we can program with this. And to operate this machine, we have to be an engineer. So the engineer can be in any kind of discipline. So first of all, we should know the knowledge about this machine. This machine consists of an electrical components as well as an electrical components as well as a mechanical as well as a software. So this is what, and we use various softwares in this machine also. So next to this room, we have a mechanical room, which the mechanical room consists of a chiller unit, air compressor unit, and a hydraulic unit. So these are all attached to the machine. So the chiller unit normally use here to cool our equipment. The hydraulic unit where we can operate the mechanical movement of our piston or whatever it is. And basically the machine operates with how the heating process is taking place is by means of resistance heating, Joule's law of heating. So this is what about this, as of now I can talk about this much about the equipment component and the system attached with this machine. And now let's go into our welding simulation, heat affected zone simulation. So I can show it here. So I have taken 4 experiments. So 2 flat specimen and 2 round cylindrical specimen. This specimen where I am going to use, this one I am going to use the simulation for CMT or GMAW, and this one is going to be for our resistance spot welding, which is going to be an high heating rate, and this one is a low heating rate. And this is going to be a simulation of our friction stir welding. So normally we call as a thermomechanically heat affected zone. So and this is the one we are going to use it for our manual metal arc welding. So these 4 experiments we have taken for our today's lab class. So the first experiment what I am going to show you is the welding of thermocouple. So since Gleeble equipment is mainly used for an high temperature testing machine, so normally we use for measuring a temperature, we use a thermocouple. So the thermocouple we have to attach physically. So and the test is going to be, and throughout our test is going to be at high temperature. So the thermocouple has to be fixed very firmly onto the sample. So first I am going to show how the thermocouples are going to be joined with our specimen. So let's move on to our thermocouple welder. So this is our spot welder. So it's a simple spot welder. We have 2 electrodes. One is positive and another one is one is positive, another one is negative. So I have a sample of this cylindrical sample. I am going to weld a thermocouple on this. I have a wire, K-type wire, 2 wire. So normally we use a K-type wire for maximum of measuring 1200 degrees centigrade, and beyond 1200 degrees centigrade normally we will go for a platinum rhodium, either a B-type or a R-type or a S-type thermocouple. So since I am not going beyond 1100 degrees centigrade, I am going to use a K-type thermocouple. and K-type thermocouple it's going to be a cheaper cost in our market, whereas comparing to a platinum rhodium it's a bit costlier. So let's use our B-type and K-type thermocouple. So for that you have to prepare this sample, you have to polish it, and you have to mark the center. So the specimen size is 86. I am going to mark it at 43 mm at center, so that at center I am going to fix the thermocouple. So the thermocouple welder operates by means of the voltage and current. So the voltage is maximum voltage we can set to the thermocouple welder is the 50 volts. So for with our experience and for this material, the voltage ranges varies from 30 volts to 50 volts. But the optimum voltage is for the welding of thermocouple to this particular material, it's going to be a 34. So let's take one wire. In general, in our normal practice, what we do, we will twist two wires and making a junction. Making a junction at one end, we will make a ball. So that forms a junction. So that is what we use it for our measuring temperature measurement. But here we are not going to twist the wire, so instead we are going to weld the thermocouple one after one. So initially I'll take one wire of our K-type thermocouple. This one is going to be a chromal. Okay, so I have fixed one wire. So as soon as I fixed, so I am going to push this button. As soon as I push this button, that spring will be released and it will be attached. Immediately the current will be passed into that. So one end will be welded, other end will be welded. So as of now I have welded one thermocouple. You can see how good it is holding. This is how we have to weld one thermocouple. So another wire I am going to weld, so leaving a gap of around 1.5 to 2 mm gap. Behind of the first thermocouple I am going to weld another wire. It is not that. The basic reason is the original thermocouple wire. How do we do that? We twist at one end and form a junction, right? Okay, so if the minimum 1 mm to 1.5 mm, if we give a gap, you can show it very closely. So this forms a junction. But otherwise what we can do, we can put a hole and you can insert it. But sometimes the reading might not be correct. So this gives you an exact reading of our temperature at our specimen. So that is why we are joining. And again, when I go to a high temperature, this thermocouple may come out also. So for that the welding of thermocouple is very very important. So that's why I have taken this is kind, and in fact you should have a very good skill to weld the thermocouple on the specimen. Okay. Yeah, see, both way you will have a junction here. That also will create a junction, and here also it forms a junction at one end. Okay, right? And you can see when I twist it, again I am inserting it, then there is a possibility of coming out, whereas you can see I am holding. So it is a very strong weld, I can say that. So it never come out. So that kind of strength welding of weld we have made on the thermocouple. Okay, shall we move on to another part? Thank you. Sorry. Okay, so the first experiment what we are going to do is the low heating rate. So we are going to simulate the heat affected zone of CMT or GMAW welding process. The last week we had a class. Okay. So last week we had measured a thermal cycle. So when I look into my thermal profile, it was around 80 C per second. 80 C per second, and the heating went up to 1100. So it went up to around 1060 or something. It went up to 1060. Not for that, I am going to a little higher temperature. So that's 1100 C per second. So I am going to simulate with one of the flat specimen. It's going to be a DP 980 steel, dual phase steel. DP 980. So I am going to simulate on this plate. Okay, so to start with, we have to fix the specimen on our grips. So we have a copper grips as well as this is a copper grip, and this one is the stainless steel grip. So since we are going to do a welding simulation, and the heating rate is the one which plays an important role for that, and I need a good electrical contact, I use a copper grip. So I am going to use a flat grip. Okay, you can able to see. Hello. Okay, thank you. So I have gripped the specimen into the copper grips, and I am going to fix this into our Gleeble equipment. So we have a chamber. Inside the chamber we have a two jaw, we say. We normally say it is a jaw. So the left hand jaw and right hand jaw. So right hand side of jaw is fixed one. The left side is the one which can be moved to and fro. You can able to see. Right. Okay, right. So in the Gleeble can measure up to 4 temperatures we can measure. So you can see here TC1, TC2, TC3 and TC4, and I am going to use only one temperature measurement. So I am going to connect only one at TC1. So here we have a positive and negative. So I have fixed the thermocouple and my temperature reads the room temperature. You can see here my sample temperature right now it reads 25 degrees centigrade. My room temperature is also 25 degrees centigrade. Okay, so I'll bring the sink lamp. So since the heating is done by our resistance heating, we have to tight very firmly. Right, so let's close the chamber, and the heat affected zone simulation I am going to do with the organ atmosphere, because I am going to take the temperature to 1100 degree. There is a formation of oxide layer, so I want to do with the organ atmosphere. So for that initially I will purge vacuum. I will create a vacuum. So let's stay for some time. Then let's move on to how to conduct this experiment. So we have a different softwares in this machine. Like right now I have programmed for this CMT welding process heat affected zone simulation. So what I am going to do is it's what you see on the computer screen. Normally we say it is a table program. So table program, I am going to have programmed the temperature to 1100 degrees centigrade. So at the rate of 80 C per second. So how much time it takes? It takes 13.75 seconds. So in 13.75 seconds, it will heat the material to 1100 degrees centigrade. And I am holding for 1 second, so it will go to the peak temperature. Then after I will switch off my power. So and I will wait for 1 minute, so to observe the how much cooling take place. So you all had seen in our welding processes, the torch will be moving, and it will when it comes at one end, it goes to peak temperature and it will be air cooled, or the furnace cooled, or whatever is it will be cooled from room temperature. So this is what we are planning to do our experiment. I'll switch on the organ. So right now I am filling the organ. Okay, so shall we start? Right? Shall we start, students? Now our first heat affected zone simulation is ready. So once I once I press the start push button, so machine will be starting immediately, and it will be end by almost 1 minute 20 seconds. So this is the program temperature, and I have a sample temperature. It is heating. I'm giving something. So now it started cooling. It went up to 1100 degrees centigrade and it started cooling. So my cooling take place. Okay, so our test is completed. So at the end, the whatever we have measured, the temperature, whatever the measurement of temperature we have done, it will be comes in our origin software. So origin software, which is the one we can plot whatever we need. So the black color shows the program temperature, and the red color where the plot shows the our temperature measured on the sample itself. So it exactly matches the program temperature versus our measured temperature. So it's went up to 1100 degrees centigrade. Let's see how much the heating rate we have achieved. So I am taking from room temperature 22 degrees centigrade, and it went up to 1195, 1100. So okay, so exactly it achieved 80 C per second. So this is what the heat affected zone simulation. So as right now we have simulated our heat affected zone simulation for our CMT building or GMA. This was the thermal profile. We got it from last week. Okay, so I could generate my heat affected zone simulation. Let's see how our sample looks like. So, in general, when I look into the heat affected zone at our CMT welding, the actual welding, I'll get very thin. Whereas here I can get this much area of heat affected zone. So I can do a very elaborate characterization with this heat affected zone simulation. Okay, right? So this is what about our first HSE simulation. The next simulation, what we are going to see is the high heating rate. So we are going to see the process called a resistance spot welding. So if you look into the resistance spot welding, the weld will be finished less than a second. So that means my heating rate will be very high heating rate. So the heating rate what we are going to do right now is for next experiment is going to be a 1000 C per second. So 1000 C per second is not that easy. So we are going to do that. So in real I am going to use a cylindrical sample. So for that I am going to use a copper once again. Copper grips I am going to use. Okay, so I am going to use a different program. So
Right.
close this. Okay, so now you can see here the same temperature I had seen, 1100 degrees centigrade, and I am going to heat it at 1000 C per second. 1000 C per second. So how much time it will take? 1.1 second it should reach in 1100, and then again I am giving for 1 second holding time. Then after I am cooling it. Let's see how this is going to do that. Vacuum photo. Right. So this is what the plot we have got for our resistance spot welding heat affected zone simulation. The black one which shows the program temperature, and the red one is the our actual temperature. So it exactly went up to our 1100 degrees centigrade. So if you want to see the heating rate whether we have achieved, yes, we have achieved 992 C per second. The slope indicates 992 C per second. So this is the power of our Gleeble for HAG simulation. So next one we will going for a experiment, friction stir welding process. Friction stir welding process where I am going to use a different program. So the material I am going to use here is the aluminum material. Right. So I have a program. So here I am going to use a mechanical also I am going to bring into this picture. So initially I will heat this specimen at the rate of 40 C per second, that is I am going up to 360 degrees centigrade, and holding it for 30 seconds, okay, so that the whole temperature will be homogeneous, and then after I am going to pull this specimen, so that is 10 mm per second. So for 20 mm I am going to pull, so that is in 2 seconds it will be pulled. Then after I will be holding and observing the temperature till room temperature, or let's see how much cooling it takes place. So for that I am going to use an aluminum sample, the dog bone sample I have prepared. depict this. You can see the HIG simulation of our resistance portfolio.
Oh, came out.
I use DP steel. Huh?
Okay, sir. Shall we turn off this video?
Yeah?
Shall we turn off this video?
Yeah, turn off. Sir. So I could not weld the thermocouple on the aluminum alloy. So for that I have shifted to DP980 steel. The same procedure I am going to do for the DP980 steel what I said for the aluminum alloy. But I am going to do it in a somewhat little higher temperature. Let's see how this test goes. So I am going to 1000 degrees centigrade. So how much 1000 degrees centigrade? 40 C per second now. It takes about 25 seconds. 25 seconds. And then I will give about 30 seconds holding. Then I will pull it to 30 mm in 3 seconds. Okay, shall we start? Okay, so we will start, but anyhow now it's going to an high pressure. That takes about 20 seconds. Then again your heating starts. It will take about 25 seconds. Then it will soak for 30 seconds. Then again it will pull. Okay, so you can slowly view this camera onto the sample itself. Started heating. Now it's 400 degrees centigrade. 550. Okay. 30 seconds to finish up. What? Tester. So, what is the thing from this test? What are we going to observe? So, initially, since it's going to be an high temperature tensile test, so first we have to check the temperature, whether I achieved the temperature or not. I have achieved up to 1000 degrees centigrade. So, that was the temperature is okay. Then again, if I want to check the heating rate, whether it is went or not. Sorry. Okay, so I could achieve 40 C per second heating rate. That also fine. Then the finally is going to be my stress versus strain. So for this sample at this temperature, I got this is the stress versus strain plot. I got maximum of 136 megapascal. So this is what you will get the results from this hot tensile testing for this flat specimen, and you can do for the cylindrical sample also for 6 mm or 10 mm rod. Okay, so any questions so far, students? Hello? Any questions? Okay, shall we go to the other experiment, the last one? Hello? Okay, so the last experiment is going to be a very good experiment for our metallurgist, I have to say that. So as and when you are doing your BTech or MTech, whatever it is, so normally for phase transformation, we used to go through the iron carbon diagram. That gives you the temperature, what are the phases, the temperature changes. But here, for phase transformation study, we are going to use a dilatometry, which is going to be an extensometer. So it's nothing but LVDT, a sensor. I am going to physically attach onto the sample. Let's see how it is done. So this test, what I am going to do is a real application study, where the material called a P91, it is a steel material which is used in our nuclear plants. The sample we received from our IGCAR Kalpakam. We are doing a project on that. Professor Murugan is doing project on that. So I am going to do a real simulation of our real application. So it is going to be very interesting. So you give me a little time, so that I have to attach the dilatometer and other things also. So kindly be on the line. Coating use பண்ணிருக்காங்க. They have used some coating. That's why it's got some fumes. Got it? Zinc coating. Zinc coated. Check. Look at the case. So black. Bindu for madam sample. Okay, so let's have a thermocouple on it. We'll use this thermocouple. What's that? So the last experiment, what we are planning to do is we are going to heat this specimen at the rate of 50 C per second. 50 C per second. So how much 50 C per second? 1100. Takes about 22 seconds. So and 1 second hold, then again I am going to come with at 500 C for cooling rate is 500 C, up to 500 C, 50 C per second. Then after I am going to 50C cooling rate. Then after I will use 10C cooling rate up to room temperature. Then I am going to put it. Let's see how it is done. So 500 to 25, 500 minus 25 is after divided by 2, it takes 31 seconds. Okay, so this is how the program I have made it. So I will heat this specimen to 1100 degrees centigrade at the rate of 50 C per second heating rate, then holding it for 1 second, then cooling it to 500 degree with the heating rate of 50 C per second, then after little slow cooling 25 C per second. Let's see how this experiment goes. So here again I am going to use a copper grip of 10 mm diameter copper grip. I will bring the So this is the dialectometer. I am going to attach. It reads plus or minus 2.54 mm cross section. Okay. Okay, this is dialectometer and I connect extensometer. I connected. Shall we start?
Yes.
Okay. Okay, so I have reached rough vacuum. Let's do with our experiment. You can either way. So our dialectometer will start reading. You can show there also. fast. Phase transformation. Cooling rate is not achieved. Okay. Still we have a temperature of about 325. So it depends on the sample size. Okay. Let's see our results, how it has come. You want to. So since it is a high temperature test, let's check the temperatures, whether it has achieved or not. Okay. It went up to our set temperature, so 1100 degrees centigrade. So our plot. Okay. So this is the plot. It shows the temperature. The dilatometer was the temperature. So you can see here our phase transformation. Here we have got a AC1. From there your phase is getting transformed, and then AC3 here. So this is the AC1 and AC3. So here you can see AC1 and AC3. So we got AC1 approximately, I can say, is 868 degrees centigrade, and here I got is 911 is the AC3 temperature. So this is what about our dilatometry measuring with our Gleeble phase transformation study. Okay. Right. So to summarize, we have done total 5 experiments. We started with the welding of thermocouple welding. Then we have went into the second experiment of HAG simulation of CMT as well as a GMAW welding process. The third experiment we have done the heat affected zone of resistance spot welding simulation. And the fourth experiment we try to do for the friction stir welding. Since it's a welding of the thermocouple with welding alloy, it's going to be tough. So again, thermocouple is not welding, and it comes here, its spot comes out. For that we have taken a TP dual phase steel, and we have done. It's called an hot tensile test. We have done with that. And fifth experiment we have done an phase transformation study while doing a welding at MMAW, manual metal arc welding. When we do, so what are the phases we will have? So that is what we have done for our today's lab class, Gleeble lab class. So any questions, please, you are welcome. So students, any questions? Earlier. Hello? Anyone is there? Hello? Hello? Yeah, so I will physically I will show you with can I switch on my camera, sir?
Yeah.
Okay. It will record. How to go with back camera? Back camera. Okay. Now we are talking. Okay, so now you are in chamber. You could see. Yeah, chamber is visible. So I am going to take the dilatometer out so that it will block you. So this is going to be my dilatometer. So it's very nice device. Okay, right. So where you are able to see two copper grips, this one and this one. Okay, right. So this is fixed with the aluminum block, both sides. Right. This aluminum blocks, the water pipeline is connected here. You can see here water pipeline. This is the where the water is coming from our chiller unit, where the cooled water is pumped into this, and with that conduction it is cooling our copper grips. From there it cools our sample also right now. So that means it is a furnace cooling. Okay, so still you want to have a further faster cooling, we can have a air quenching setup. So that has got a different setup we have that we can attach with this machine. So whenever you want to have a cooling, that time the air will be sprayed on that, so we can do that. So still further you want to have, we can use a water quenching also, but right now we cannot use the organ or helium cooling for our cooling purpose. Okay. No, actually the machine is capable of doing 10,000 C per second heating rate, and cooling rate is also possible. Okay, but here if you see here, the sample size is 120 mm. Okay, so if I further reduce the gauge length, my cooling rate will be fast. So according to our cooling rate and heating rate, we can design our own sample and we can fix and to achieve for that actually. But I said that earlier, this is the sample I received from IGCAR Kalpakam. So they want to do it for this specimen. In fact, when I was trying and they were asking for the 50 C per second cooling rate, For this diameter, they are not getting the cooling rate, so they have changed the specimen dimension as per our request. You can see this is a normal sample, and they have designed like dog bone. Center, they have reduced the diameter to 4.5 mm. There you can achieve the cooling rate what they expected. Hope I cleared my doubt. Cleared your doubt? Okay. Okay. So any other questions? Okay. So apart from this heat affected zone simulation, so this Gleeble is mainly used for a weldability study. Weldability study is like outside of this Gleeble, we are for weldability test we use a Verastrain test. Normally Verastrain test. So you can whenever you visit our lab, you can see the Verastrain test equipment also. So apart from Verastrain test, you can have use our Gleeble also. So for that, we will normally say it is a nil strength test, nil ductility temperature test, and ductility recovery temperature test. So these three tests we normally conduct to test for weldability test. So that gives you an exactly the exact okay. So exactly it will give you a weldability, how whether my designed alloy is going to be a weldable or not. So it's called an weldability test. So this is one of the application we can use in our Gleeble. So various applications also is there. So our Professor Murugan sir is using all the application, I can say that. Any other thing you want to know from us, sir? Okay, so shall we close? How about students, shall we close the lab class? Okay, right. So let's stop for today's lab class and see you in the next week. Next week we are going to have a plasma arc welding, microplasma arc welding, and magnetically impelled arc butt welding. That's called a MEAP. So three lab process we are going to show you. So before coming to next class, you please look into the website or whatever it is. So you please go through the literatures or whatever it is, so that you can understand the next class welding processes very easily. And anyhow, one new process what you are going to see is called the MEAP. It is a really very good machine. Earlier we had a flash butt welding equipment. So instead of flash butt welding equipment, nowadays we started using MEAP. So that also going to be a very good experiment for you for next class. So let's finish off our today's class. And I would like to say thanks to our professor and our JAM lab team, Mr. Prakash, Mr. Jay, who is that? Jag, and Soma madam, and the Niveta madam, and Surya Kumar sir, and again our Rajesh sir. So and each and all our team, I would like to thank them. Okay, so thank you. See you, students. Bye bye. Thank you, sir.